Hello everyone, my name is Pedro and I'm going to present an SDN-based framework for slice orchestration using in-band network telemetry in 802.11 radio access networks. First of all, our framework is built in an SDN-enabled 5G infrastructure at the Industrial IoT Lab located in Ghent, Belgium. 3 access points were installed to compose the wireless termination points, while 9 Intel NUCs are used as stations. In addition, a single computer connected to the wired segment is used to host all network controllers. Here there's an overview of our framework within the SDN management plane. As illustrated, we rely on 5G NPower and Brio controllers to perform changes in the network, as well as on Grafana and Postgres for data visualization. So let's check out the framework. Once we authenticate, there are 2 possible actions we can perform: manage resources and visualize them. Those options include to manage controllers, tenants, and interactive graphs. Here, different controllers can be managed. Possibly hosted on different IP addresses and ports, we can easily modify those parameters as well as the authentication credentials used to interact with them. We can also specify the controller type, leaving the possibility for further extensions. Multiple tenants might share the same controller. Therefore, they can be managed via this interface. To integrate the interactive graph visualizations within our framework, we can specify the necessary parameters to access the Grafana panels. We can specify the controller, a name for the graph, the iframe URL, and also a type for the graph. As soon as this information is set and our controllers are up and running with our customized monitoring and control applications, we can access the data plane visualization. Besides visualizing, we can perform slice orchestration and other management tasks. Here, at the top left corner, we can check which tenant is being shown, followed by the legend for the topology graph. At the top right corner of the screen, we have the buttons for the monitoring and the management panels. I'm setting the pooling frequency to 5 seconds, so topology, slice, and application information should be gathered soon. Now, the topology has synced, but since there are no active flows in the network, the interactive graphs show no monitoring information. By accessing the network management panel, we can check and modify slice configurations at runtime. In addition, we can visualize the traffic rules defined at the controllers and the application requirements that are reported by the stations. When a station has to start a flow belonging to a certain application, the first step is to publish application requirements towards the network controller. And after that, the station can begin sending network traffic. As we can see, a burst of packets is initiated between 2 stations, and the fine-grained end-to-end monitoring information from our in-band network telemetry can be seen already on the interactive graphs. The information we can see there includes 2 sets of graphs, one representing information per application and the other per node. The end-to-end jitter and latency are per application, while the channel, data rate reported by the driver, the MCS, processing delay, RSSI, and retransmission flag are per node. Now we are running two different applications between two different pairs of stations. Application 1 has a 1 megabit per second of UDP traffic, while application 2 has 4 megabit per second throughput. We can see that for both applications, the end-to-end latency is around 100 to 200 milliseconds. So, we are going to decrease the airtime of the slice handling application 2, hoping that application 1 gets better quality of service. In this case, we perform network slicing at runtime. Although we have other configurations, such as the AMSDU aggregation and the priority scheduler, we have only set the portion of airtime, named quantum. The quantum defines the portion of airtime which is allocated to the slice at each transmission round in the scheduler of the access point. We have set a very low value for the slice handling application 2, and we see that the quantum value has changed accordingly. Also, we immediately see the impact on the end-to-end latency of both applications. Both have decreased and remain lower than 10 milliseconds. We see that because now packets from application 2 are being held within its queue, that the processing delay has increased a little, and the data rate reported by the driver is lower than previously. Also, by checking the downlink traffic of each slice on each access point, we can see the moment where the slice where application 2 is flowing has been modified. In this case, the flow of 4 megabits per second has now only around 1.5 megabits per second of throughput. If we set back the default configuration, we can see that the previous end-to-end latencies and throughput will be what they were before. To perform network slicing dynamically, we can activate and configure an algorithm we have developed at the controller to check for application requirements and then change slice configurations in a loop fashion. We can specify the minimum, maximum, increase and decrease rates that dictate the pace and the boundaries for the adaptation algorithm. From this moment, slices will have their quantum adapted dynamically by the application. As we can see on the graphs, the quantum of the slice where application 2 is flowing is gradually decreasing, based on the configuration parameters we set. And this only happens because we have very strict requirements for jitter and latency on application 1, which is running on the same access point as application 2. After a while, similar results are achieved for both end-to-end latency and throughput. Therefore, to address management of multiple networks and applications in such programmable wireless environment, our framework comes in handy. With the fine-grained monitor information gathered via In-Band Network Telemetry, time-critical applications can be verified, while the possibilities for research here are endless. Thank you for your time, and please contact us for any further information.